All right. Hi, everybody. This is Noah with Learn Meta Analysis. A number of you have been asking for a video on how to do three-level meta-analysis with correlated and hierarchical effects and robust variance estimation. And I finally have had time to do that. So before we get into the video, I'm going to do a shameless plug for my own GUI-based software, Simple Meta-Analysis. This is Simple Meta-Analysis here. If you want to do the analysis very quickly, this will help you do that. For an example, you just click on Run Analysis, you click to open this, and let's see, then we go here, we choose our file, we click Run, and we're done. Okay, and you can download all this, and it gives you the sensitivity analysis here, and it gives you the R script customized for your code. So note how quick that was, because this is so much faster than the code I'm about to show you guys now. So let me show you how to do this in R, in case you're like me and like knowing how everything works behind the scenes. So if you remember, the first thing we're going to do in R is we're going to set our working directory. So we're just going to open up Session. We're going to go to Set Working Directory. And in this case, I'm just going to choose my source file location. And you can see that worked down here. Now I'm going to read in my data. Whoops, I forgot to say what kind of data file this is. Okay. So I've included the data file in the GitHub repo, which is linked in the description. So I guess the first thing we should do is load our packages. I actually already did this, but I'm going to do it again anyway, just for completeness. Then we're going to read in our data, which is here. Whoops, sorry about that. Okay, read in our data. Okay, you can see that worked and it showed up over here in our environment. You can see we have all this good information. If you're wondering about how to format your data file for three-level meta-analysis in this format, it's going to be the same as you would do in a regular three-level meta-analysis. I've already made a video on that, so I'll include the link in the description in case you want to know how to format your data. But for three-level meta-analysis, you're going to format your data the same if it's using correlated and hierarchical effects and robust variance estimation, or if it is using just the regular three-level model. So if we look over here, we can see that this data set includes mean, standard deviation, sample sizes, but it does not actually include our effect sizes. So we're going to calculate that real quick using this script, which we've covered in other videos. What did I break here? Oh, yeah. Okay, this is what I broke. I had the wrong data name in there. Should be dat1. Okay, save that, rerun it. Sorry, it's been a long day, and I am only human, so I make mistakes sometimes. We'll look and see, and you can see now we have the Y column, YI, and we have our variance column, VI. Wonderful. All right, so I'm going to minimize things over here in my environment just so it's a little easier to read, but you can see in our original data set, 35 observations of 23 variables. Now that we've calculated the effect size and the variance for each one, we have 35 observations of 25 variables. That's exactly what we want. And as you guys know, I like to save this file with my effect size data so that I don't ever have to do that step again, because I don't know why. For some reason, that step is both wonderful in the sense of it calculates all the effect size and variance very, very quickly, but I also find it really annoying to have to do that. And I honestly don't know why I find that so annoying, but I always like to save my file so that I never have to do that part again. Okay, so the thing that's a little bit different about what we're doing now, so the three-level meta-analysis essentially, I should have created, I should have pulled up some nice graphics here, but that's okay. So in our three-level meta-analysis, we're accounting for the hierarchical structure, but not necessarily the correlation between the effect sizes. And if you're investigating using three-level meta-analysis with correlated and hierarchical effects and robust variance estimation, my guess is you at least have some sort of understanding, at least a basic understanding of how that hierarchical structure works and why the correlated effects can be important in some cases. In case you're not, or in case you want to refresh your memory, I'm going to include a link in the description to the book Doing Meta-Analysis in R by I think it's Harrer et al. It's an open book. It's free. All you got to do is click the link, and it brings you to their book down page, and you can read it right there online. No downloads required or anything like that. I think they do a very nice job explaining why you might want to use this structure in your analysis, and I originally got the code that we're going to use from there. The difference between what you're going to see in this video and the code that they provide is they provide the code using the clubSandwich package, which uses, I think it's impute covariance matrices or something to that effect is the function. But that's been deprecated, and so now that that's been deprecated, we're going to use the vcalc function instead. So I think Wolfgang may have an example using vcalc on the metafor site. I'm sure he does. He has awesome documentation on there. But I'm going to show you guys how to use that method to set up this structure. So the first thing that we're going to do is set up our row value, and this is essentially our correlation here that we want to account for. So I'm going to set row at 0.6, and I'm going to hit run. So all that does is that's just saying, hey, anytime you see the word row, that actually means a value of 0.6. That's basically what we're defining right there. Next, we're going to set up our covariance matrix for row. So what we're going to do is, if you recall the way R structures this, I like to think of, I'm going to name this V, capital V, and then what am I going to name that? Well, everything that comes after this little arrow. So we're going to use the VCalc function for metafor. We're going to say our variance column of our effect sizes is our first value here. Next, we're going to tell it the cluster is labeled study in our data set. The observation is labeled effect size number in our data set. The data is in the data set called data, because I'm really creative. Last but not least, we have row, and we are going to set our row value as row. And I do this intentionally, like leaving things called data and row, just because I find it easier. The same reason that when I look over here at what my cluster is called, I think of studies as clusters, and I think of effect sizes as going within studies. So it makes sense to me that they'd be the observations. So that's why I name things the way that I do. So we're going to go ahead and we're going to run this step. And what it's going to do is over here on the right hand side in our environment, you can see we now have this V matrix, right? It's got a bunch of numbers in it, and we're just going to leave that closed. I don't see any reason to open that. But now that's there. So next we are going to actually run our analysis. The first thing that we're going to do is the correlated and hierarchical effects piece, okay, with this 3-level meta-analysis. So we're going to be using a random effects model, which we can tell because we have RMA, and then we're going to use a 3-level model, and so we want to have the .mv afterwards. Our effect size is yi. Our v is different. Okay, so normally if this were a regular meta-analysis, we'd use the lowercase vi in our data set for the variances. But instead, what we're going to do here is use that one we just calculated with the covariance matrix. So we're going to use that capital V. Then just like in a regular 3-level meta-analysis, we're going to set random as the little squiggle line 1 with a bar, study, and effect size numbers, saying that we are nesting effect size numbers within studies. Next, we go down to method. We're going to use REML. For our test, we're going to use T. Our degrees of freedom, we're going to use contain. Data is our data, and sparse equals true, and this just gives us a little less information that we may not need. So let's go ahead and run this. Okay, so down here, it's saying we disregarded sparse. Okay, so just don't worry. I just wouldn't worry about it. I mean, you can take that out. It's going to do the same thing. I just leave it there for completeness because I like it. So, okay, let's move on so I don't ramble. Okay, so as you can see, it didn't give us our actual result right there. But if we want to see our result, if you recall, all we got to do is type in CHE result, which is what we named it, click run, and that's going to give us the overall meta-analytic result. So this is our result using correlated and hierarchical effects. This is not our result using robust variance estimation. So we need to do the robust variance estimation next. So that's what we're going to do. So I'm going to call this CHE result robust, so that way I know this is the robust result. And the way that we do that is we use the robust function, and the first piece we want is the result from that 3-level analysis. So we're just going to put that there. And then we have a similar setup before. We tell it the cluster number is the study. Next, we tell it that we have this argument that's like, do we want to use the clubSandwich package? And the answer is yes, we do want to use the clubSandwich package to help us with the robust variance estimation. So we're going to put true. And then for digits, I like to have 3 just because it helps me know. I just like 3 digits after a decimal point. I guess I don't really have a good explanation for why I like that. I just do. That's what I've always done. So I'm going to go ahead and highlight this, and I am going to run it, and we can see what we will get. Okay, so here we have our result, and as always, well, I shouldn't say as always, as with the 3-level meta-analysis, you're going to have a lot of the same results here, right? So we see our tau squared up here. It gives us our heterogeneity with between studies is the first one, the 2.1, and within studies is the 2.2. And then we move into our heterogeneity, and you can see in this case we have significant heterogeneity because our p-value is significant. We have 35 estimates that fell within 12 clusters, which is consistent with our data set. You can go check if you wanted to, but I'm not going to bother to do that. And then down here in the results, you can see we have an overall effect size of negative 0.345, and it is Not significant. How sad. Okay, so this is not significant. But that's really all there is to it for running a 3-level meta-analysis with correlated and hierarchical effects and robust variance estimation. So again, I just want to show you in the code what the kind of special pieces are that differentiate this from a regular 3-level analysis. First, we're going to define our rho value, and then we're going to use that to calculate our covariance matrix. Then we're going to plug that in down here as the variance of the effect size. The other piece that's different is we're going to then use robust variance estimation, and we are going to rerun this. I shouldn't say rerun this, sorry. We're going to use the robust function, and we're going to plug in that result as a point in our argument, and then we're going to actually go ahead and run this script. Thing to be careful of is, of course, make sure you don't misinterpret, right? So what I mean by that is if you decide to print the overall CHE result without the robust variance estimation, it's going to look very similar in your results section down here as the one with robust variance estimation. So let's take a look actually at this particular example and see what's different. So in this case, our model result previously was 0.34, and down here when we add robust variance estimation, it's 0.345. And I think that's the same as it was there. Yeah. So really not a lot of difference in our overall result. And I'm looking at heterogeneity. It's also very, very similar. So in this particular case, it didn't make a ton of difference. But what we can do is we normally, well, I shouldn't say normally. In most cases, if I'm using robust variance estimation, I would say I'm confident I want to use it. I know why I want to use it. I have a statistical reason why I want to use it. So I typically don't print that CHE result. So I'm going to go ahead and I'm going to delete that. The first thing that I would actually be looking for of meaning to me in this would be the result with robust variance estimation. So the next thing that we want to do is you're probably asking yourself, well, how do we come up with rho? Well, sometimes rho can be known or rho can be calculated, but in other cases, you may not know what the correlation is between measures within studies. So the guidance that I've read is that number one, we make our best guess, and then if it can't be calculated. And then number two, we can check with sensitivity analyses to see how much impact this guess has on our overall result. So in my field, it's pretty common to have a large a large correlation between measures within studies. So I'm going to just leave that at 0.6, but I might want to know what happens when we set rho at 0.4. So what I'm going to do is I'm just going to highlight this whole chunk here, and all this is doing is I'm changing the rho value. I'm calling it something different. I'm running the same analysis again. The difference is I'm just using that lower rho value. So I'm going to go ahead and I'm going to hit run. Okay, so previously our effect size was minus 0.345. And after we lower it, it's now minus 0.358. So you can see it did shift a little bit from 345 to 358, but that's not really a very large or substantial shift. So that's not too crazy. Now let's go the opposite direction, okay? So we used a correlation that was 0.2 lower before. Now let's try a correlation that's 0.2 higher. So this is with a correlation of 0.8, and we're just gonna run this section of code. All right, so now you can see our estimate is minus 0.33. So that is a little bit different yet than minus 0.34, but what we can see is that in this case, in my personal opinion, changing the rho value anywhere from 0.4 to 0.8 is really not having that significant of an effect on our overall effect size, because what we're seeing is our overall effect size is only shifting by about the hundredths place. In the meta-analyses that I have done, a change in the hundredths place is not likely to have a significant impact on the conclusions that we are drawing from that study. Moreover, you can see that the p-value here, again, is not significant, and if we look at the previous one, it was still the same at 0.456. So, yeah, really not much to see here. What we can see is that anywhere from the correlation being set at 0.4 to 0.8, we're seeing pretty consistent results. So what that would tell me is it's not that sensitive to us changing it. All right, so now let's roll into variance and understanding I squared, okay? So when we think about heterogeneity here, we already know that our sample is heterogeneous, right? Because we look at our Q-test and our p-value was statistically significant here. So we know that we have some heterogeneity, but we don't necessarily know what that's coming from. If we think about our tau squared values, we can see that it's likely coming from between studies, right? So we're gonna just we're gonna try and quantify this a little bit different way. So what we're going to do is I'm just going to highlight this script here, and I'm going to copy that, and I am going to paste it into a window. Okay, so you can see we have this huge amount of code. This teaches it how to do the analysis that we want to do. So I'm just gonna copy that. I'm gonna go down here in my console, and I'm gonna hit paste, and I'm gonna hit enter. And what that does is that teaches R how to do this calculation. So what I'm going to do now is I am actually going to run this analysis. But first, I just remembered I don't actually have anything called mmulti in this data set. So I need to go back and see what I called that particular thing. So if I remember correctly, this does not work with robust variance estimation, but we can try it just in case. I remember things wrong sometimes because I'm human and that happens. So, okay, so here we go. Our original model was called CHE result robust, and I'm just going to copy paste that in there and see what happens. Highlight it and hit run. And yeah, see, it doesn't work because it has to be an RMA.mv. That's what I thought was going to happen. So really what we need to use here is this CHE result. And so when we're looking at I squared, this is not going to be telling us the result that has the robust variance estimation. But as we saw earlier, robust variance estimation with this particular data set doesn't really make a terribly large difference, right? The overall results were pretty much the same as when we just used the correlated and hierarchical effects. So we're going to use this correlated and hierarchical effects model, and we're going to go ahead and run this and see where, oh goodness, I forgot to run ggplot. I'm sorry, R, you probably got a little mad at me right there. I think it's actually ggplot2. It's been a while. Yep. Okay, so ggplot2 is now there, and we will run this again. Wonderful. Okay, so we have our nice little diagram over here, and over here on the left-hand side, this is what I prefer to look at. I don't really know why. I can't really tell you why I don't like the picture that much. The picture is great. It tells us this really good information, but for my own purposes, when I'm running a meta-analysis, I actually prefer to look at the results that are written in text form. So you can see here at level 3, we have 86% of the variance coming from that. And with this is the between study heterogeneity is our level 3, and our level 2 is our within study heterogeneity. And recall that these are actually in the opposite order of what the results are given to us as when we look at this table. So when we look at our overall result from running the robust effect, you can see that we have sigma 2.1, and that's our between study heterogeneity. And you can see that this is larger than the within study heterogeneity. And when we go down to our I squared results, we see that those match, right? Because we have our level 3 at 86%, and we have our level 2 at 10%. And the 10% is corresponding to our within study heterogeneity, and within study variation, and level 3 is going to our between. Overall, we have 96.81%. Okay, that gets us through that, and we will move on. Okay, so let's check out the outliers and influence statistics. Now, caveat with this, as with every time I talk about outliers and influence, is there, at least to my knowledge, there's not really a great way to identify what a significant outlier is or what significant influence might be in these meta-analyses with dependent effect sizes. So we're going to do the best we can. And so the first thing that I'm going to do is I am actually just going to rerun this, and I'm realizing I need to swap out this model code. It was CHE result, and I'm just going to copy paste this in a couple of other places. You guys won't have to worry about this because this will be in the code in GitHub by the time you guys see it. Okay, so the first thing I'm going to do is just compute my robust result again, and the reason is just because Just because I like to. I like to have a result in each section. I don't know why. When I'm doing lots of coding, I find it to be helpful. In this case, like I honestly just grabbed all these codes directly out of simple meta-analysis. Like I ran all of this data through simple meta-analysis just so I get the R script because I was too lazy to actually type all of this out. And simple meta-analysis gives you the R script for every single analysis that you do. So it was just much faster, and that's why some of these are have different names. It's just because of the way that's programmed. Okay. Anyway, enough of me rambling. So we've recalculated our robust effect, and now we're going to do our outlier analysis. So I'm going to first run this. Wonderful. Now I'm going to calculate my Cook's distances, and I guess I should probably explain what we're doing here. I'm sorry. Long story short, we're looking for confidence intervals that don't overlap with the meta-analytic confidence interval. That's essentially what we're doing here. I'm not going to go into all the 1.96 and all that stuff because you guys hopefully know statistics by now. Hopefully understand statistics. Okay, so moving on. Next, we're going to calculate our Cook's distance. I'm going to call it Cook's, and I'm going to use the Cook's.distance function, and I'm going to use that on our robust effect. So then I'm going to move down, and I'm going to start calculating df betas. So, peculiar. Okay. I'm going to come back to this line because I don't remember why I put this line under calculate df betas. So we're going to start on the df betas. So something that I want to mention, actually, I'm just going to move this so that you guys don't get confused from it, because if it confused me right there, it would probably confuse you too. Let me just label this. Okay, so the first thing we're going to do is calculate df betas. We do that by using the df betas function. Something that I want to point out is that we're using the correlated and hierarchical effect result here, not the robust result. The other thing that I want to mention is I have seen people say that we should instead be looking for outliers and influence in that working model, the correlated and hierarchical effects model, rather than the robust model. So depending upon where you fall on that, you can just simply change out these interchangeably. So if you want to use your CHE model instead, you just put the name of the CHE model instead of the name of your robust model here. But for our purposes right now, we're going to use the robust model to calculate Cook's distance. We're going to use the CHE model to calculate our df betas. And last but not least, we're going to use our robust model again to calculate our hat values. And then what we're going to do is we're going to try and detect these things automatically. So we are going to run this script here, which is calculating what the hat value should be to be marked as an outlier, or I'm sorry, an influential study. Then we're going to tie together all of these wonderful things. We are going to adjust the column names, and we're going to add a row that reminds us later that the df betas is based on the 3-level CHE model and not the 3-level CHE RVE model. And then we're going to highlight that whole thing and click run. Okay, so what we can see here is a very large data set that looks very weird in the R console, but that's okay. We can make do. Sometimes it displays a little bit funny like this. So the first thing that I'm looking at is this outlier column, and you can see this outlier column has a number that are labeled true, right? So the next thing that I'm going to do is scroll down, and I am going to look at my Cook's flag column. I don't have anything with an asterisk here. I'm going to look at my df betas flag column. I don't have anything marked here, and I don't have anything marked as hat flag either. So from there, I can see I have 3 potential outliers, and normally what I would do is I would go back and actually examine these things and see why might these be outliers. So you can see, for example, this effect size is quite small compared to even this other next outlier at -4. So you can see we do have some extreme effect sizes here. In this case, these are valid effect sizes. This is what the study actually found. The study was not notably different than others in the sample. And so in this case, especially since these were not influential studies, so if you look down here at our Cook's, df beta, and hat flag, they were not significant, so they were not significantly influential. In this case, I actually left these the same as they are. I did not downsize them. I did not change them. I just acknowledged that they were outliers and moved on. Okay, so next I'm going to show you guys how to do a moderator analysis. And this is going to be categorical. Okay, so the first thing that I want to mention is that when I started doing these and exploring these different models, I found that in some cases I would not actually get a overall result in terms of a Q statistic. And so if I remember correctly, I ended up asking on the R message board, which is the special interest group email list for meta-analysis in R, is absolutely wonderful. There are some very, 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 very helpful people on there, and there's so much great information there. I'm going to try and remember to put a link in the description so that you guys can go, and if you are interested in doing meta-analysis in R, I very much encourage you to join. Even if you never actually write anything, it's great to just read what other people are talking about. I have learned so much about meta-analysis from reading about other people's analyses and the questions that they're having and how people are suggesting that they approach them. It's been a really positive experience for me being on that email list, and it doesn't overwhelm your email either. I think I get 1 email a day from it. Okay, so anyway, to the point. The first thing that I found was that when I had one or like when I would have moderators that only have one row, like one, I'm sorry, what's the word I'm looking for? One comparison. When there was only one comparison at the whole level of the moderator, then I wouldn't get an overall Q statistic. And so what I ended up doing was removing those. And so that's what this first piece does. This first piece excludes levels. So I just realized my moderator name is wrong because I copied that from a different data set. So let me copy this here. Okay. So what this is going to do is this is going to look at your moderator. In this case, we're going to use Control C, which is our control group that we're comparing to. And we are going to drop if there is any that is 1 or less. So, and then we're going to put this in new filtered data into a new item called filtered data. That's probably a really poor explanation. And I'm sorry, I know I'm a little bit rambly right now, but it's because I'm tired. It's Friday night. And I'm coding for some reason. I don't know why I'm coding on a Friday night. But anyway, what we're doing is we're taking all of our, for this moderator, we're looking to see if there's any levels with 1 or less comparisons. And if there are, we're removing them from the data set. And then we're creating this new item called filtered data that excludes those levels of the moderator. So that's what I'm going to do first. Oh, I forgot to, okay. There's another library I forgot. I forgot to run, I think it's probably pronounced deployer, but I like to call it deployer. I just find it more fun to say. So we need to load deployer for this to work. So we'll scroll back down here and we will run this again. Okay, wonderful. So that worked. So we know this worked. In case you're wondering, over here on the right, you can see I now have filtered data labeled over here. So I've used my moderator variable Control C. I've dropped that into a few places here. The next thing that I want to do is I want to impute my covariance matrix again. So I'm again going to set my row at 0.6. This is consistent with my overall analysis. Then I am going to use that to calculate my covariance matrix, and I am going to do that this time using the filtered data. Okay, so that's the big change I want you to see here. Number one, we're still using row, and because it's 0.6, I actually just left it called the same thing. And then for the data, this is the piece we need to change because we're using filtered data, which we just calculated. So let's go ahead and hit run. Okay, so we can see that worked. Next, we want to run our meta-analysis with the intercept. Okay, so let me walk you through what we're doing here. If you recall, when we run a categorical moderator analysis with metafor, there's 2 different tests that you can see as the test of moderator, depending upon if you include or exclude the intercept. So when you include the intercept, it's going to tell you if there's a difference between levels, whereas when you exclude the intercept, it's going to tell you if they're significantly different than 0. So in this case, what we want to know is, are there significant differences between level of the moderator? So what we're going to do first is we're going to run this same meta-analysis with correlated and hierarchical effects and robust variance estimation, and we are then going to look for that Q value, or that test of moderator value, to see if there is significant difference between levels. So the first step that we're going to do, we are going to run, I'm going to call this result underscore Tom, and Tom in this case stands for test of moderator in my mind. So we're going to use rma.mv again. This is the same. Now, this is where things get a little bit different, okay? For our effect size, we're using the filtered data effect size. So we need to have filtered data in front with a $sign to tell it what specific column to look for, which is yi. Then for our variance component, we're going to use this VRVE that we just calculated right here. Then we set up our typical moderator string with the little squiggly line. We are doing categorical analysis, or categorical moderator variable. So we're going to include factor at the beginning. We're going to say in the filtered data set, we want to use control C, which is our moderator variable. Then we set up this random with the -1, and we have this line, and then we have our study nested with effect sizes nested within them. Then we are going to use REML, the t-test, and the data, again, is going to be filtered data. Okay, so we're going to use that filtered data. So this is exactly the same as what you saw up above, with the exception of we swapped out filtered data and we swapped out this and we added the moderators. But it doesn't matter in terms of coding if you put it all in one line like this, or if you hit enter between things like this and put each one on its own line. It's gonna all run the same. So, whoops, I must have really... Sorry, I hit Control Z and it went back a few steps. Okay, so let's go back here. We are going to actually run this now and see what we have. So let's go ahead and run. Oh, I didn't explain the second line. Sorry. The second line is just adding the robust variance estimation component to it. So the first one is going to calculate our 3-level CAG model. The second one is going to use the robust variance estimation functions from clubSandwich to then get our result with robust variance estimation. Okay, so let's dissect this a bit. First and foremost, we have our tau squared up here, just like normal, and then we have our test for residual heterogeneity. Okay, that's really interesting. P-value is significant. And then we have our test of moderators. And again, this is what we are really paying attention to first, at least this is what I would be paying attention to first, is do we have significant differences between levels of our data? And the answer in this case is no. We do not see significant differences between levels of our data. And then this makes sense to me, given that we have significant residual heterogeneity. There's something else in our sample that explains the variance. So what I would want to do then is I would then want to make a table out of this. And in my field, when we tend to use categorical variables like this, we don't want it to display it typically as an intercept. Instead, we want to see what all of the actual names of the different variables are. So that's what we're going to do in this next step, is we are just going to remove that intercept to get the little bit cleaner table. And so this looks very, very similar to above. The main difference we have here is this -1 in the mod string. Okay, so I'm not going to explain the rest of that because it's essentially identical other than that -1. So I'm going to go ahead and hit run. And you can see here, again, well, I just want to remind you, this test of moderators it changed, right? Because it's different. I am ignoring this one because it is not important to me right now for what I'm trying to know. Instead, the only reason I ran this second analysis is for the model results in this table, right? Because now we have traditional training, traditional video, and virtual reality, and we have our estimates for each one, instead of having one of them be the intercept and then have to calculate what these things are. So, okay. That's that. You can tell I copy pasted outliers and influence. Let me see what we're doing here. Okay, in this next section, we are doing plots. Okay, so let's rerun these. Again, like I said, I like to just rerun my analyses each time, so mostly so I don't have to like do a lot of scrolling. And honestly, in my brain, this whole environment section doesn't really exist. So I mean, I know it's there and I know it's important, blah blah blah, but when I'm practically working on something in R, I like to be able to just scroll up a little bit and see what my items were called. And so that's why I rerun my analysis in each section. So I'm just going to rerun my analysis, and this, what does this say? Why does this say with intercept? You can see I copy pasted things. I'm going to delete that part because it's not important. Okay, so we're going to run our meta-analysis, and with CAG and robust variance estimation. Okay, and I realize there's a problem. Okay, so you see where I have this VRVE. Sorry, I probably should have proofed these before I started recording, because you guys are going to be like, man, this guy makes a lot of mistakes. Well, you know what? Thing is, I made this code super quick, and that is why. So this is where the inconsistency is. In our original code, we just called it V, right? And then later, with what we just did, we created the one with filtered data and we called it VRVE. And we don't want that. We want our original one. So I'm just going to do that. And that will correct us here. So now what we are doing is we are going to start creating our plots. And so you might be asking yourself, what do we do about publication bias? How do we detect publication bias with these dependent meta-analyses? The answer is we don't really know. Okay, so there isn't really much research out there yet on how to detect publication bias and different things like missing studies, so we don't really have that for dependent models. So what we can do is we can actually just create funnel plots, and that's pretty much it at this point that I know of. I will say there was very recently, like within the last maybe like 48 to 72 hours from the time I'm recording this, conversation on that R group about these types of things. And I know there are some researchers who are working actively on trying to detect missing studies and such in these dependent models. So again, if I remember, I'm going to include a link directly to that conversation in the description because I think you might find it helpful. So, okay, let's go ahead and run this. Okay, so this first step is just rerunning my meta-analyses again, just so that it's here and I know what things are called. So I called this robust result. And what I want to do now is I want to actually create my forest plot. So let's go ahead and do that with this code. Ta-da! Okay, so this is just a generic standard forest plot, okay? As you can see, we have all of our comparisons listed here, and this is kind of difficult, in my opinion, to understand. It makes it a little bit complex. So you can see I accidentally doubled this row, so let me get rid of the extra. And I'm going to label this create forest plot. Okay, so now we have our comparison level forest plot and we can look at that. Earlier I said this was the funnel plot, but it wasn't. Funnel plot's later. Okay, so now let us do our aggregated data. And so what I mean by this is when we look over here, you can see we have Abadia et al. Twice, Ariza et al. 3 times. And so instead, we might want to know what the effect sizes were by study instead of by comparison. So what we can do is we can first aggregate this data. Okay, so that's what we're going to do in this next step is we're going to aggregate it based on the study itself. So I'm going to go ahead and hit run. And then I'm going to impute my covariance matrix for that aggregated data. So I'm going to go ahead and hit run. Unexpected symbol. Oh, got it. There we go. I didn't highlight everything, so it tried to read it in as a command instead of as a comment. Okay, so now we have calculated, we first aggregated our data, and then we've calculated the new covariance matrix for that I keep saying aggravated. For that aggregated data. I am sorry, people. I probably shouldn't record these videos at nighttime when I'm tired after working all day. Okay, so we have the aggregated data and we have the aggregated covariance matrix. So now what we're going to do is we're going to run our 3-level meta-analysis and our robust variance estimation using this new data. So I'm going to go ahead and I'm going to do that. And then last but not least, I'm going to generate a forest plot with that new data. Boom, there we go. Okay, so that gives us our forest plot by study now instead of by comparison level. So in these 3-level analyses, I prefer to have both. I think it's important to look at both. I like looking at both. I would suggest that you do the same. So let me just check one more thing here and see. Sorry, I just realized that I had left out the funnel plot. I got through all this and realized that I left out the funnel plot. And then I got to thinking, maybe I actually deleted the funnel plot instead of I thought the forest plot was in there twice, but I think it was actually the funnel plot. So let's make that funnel plot real quick. I just dropped the code back in here again, and you can see it's all essentially the same. That is exactly what I did before, I'm realizing now. Oh, goodness. Okay, so let's run this. We're going to create that funnel plot just so that we can look at it. And this can be interpreted the same way as funnel plots for for regular meta-analysis or three-level meta-analysis as well. You can see in this case we have pretty substantial asymmetry, right? So you can see the overall effect size here in the center, and then you can see we have a ton more studies on the right side than we do on the left side. And then down here at the bottom we have way negative significant effect and nothing over there on the right. So we do have something going on with this particular data set. So yeah, okay, so I believe that has wrapped up how to do everything in R. The one thing I did not go through was how to change the moderator analysis code, but I am hoping two things. Number one, if you are this far into using R for meta-analysis, I hope that you know how to swap out which moderator is being used. Number two, I have other videos on how to do that for a three-level analysis that I think should be relatively generalizable. But real quick overview, let me find where it is in here and I'll show you what we need to swap. Okay, all these places that have Control C right now, so we have one here, we have one here, we have one here, we have one here, so we had 4 of them, right? So all of those would need to be swapped out for your different moderators as you want to test your different moderators. And if you want to test categorical moderators, you do it the way that we showed here. If you're going to do continuous moderators, typically speaking, you would leave the intercept in the model and you wouldn't do this second step of removing it from the model. And then I'm trying to think if there's anything else you may want to know about that. I guess the last thing that I'll say is if I was running multiple moderators in this data set, what I would do is I would name all of these items individually. So like I would have excluded levels underscore Control C, filter data underscore Control C, and I would replace all those throughout. Yeah, it's even going to be a matter of repeating this because you need to tell it which data to use here. So this could very easily be tedious. So as you can see, or you can probably see, these types of analyses, I mean, how many lines are we at here? We're at 200 lines of code, and all we did was very, very, very basic stuff, right? We didn't even get into multiple moderators, and sometimes you might be looking at 20 or 30 different moderator analyses. And we also didn't even talk about how to get the tables out of R into something more usable for you, which I've covered in other videos. The code can be largely moved over to this. But long story short, the reason I created simple meta-analysis was because I did a meta-analysis where I ended up having like 2,000 lines of code. And it took me way too long, and I thought there must be a better way. And when I found that there wasn't, I decided to make one because we have this wonderful packet, these wonderful R packages of Metafor and clubSandwich, and they're very, very good at helping us do statistics. But if you're not a programmer, this can be really challenging to do. And even if you're a nerd like me who likes doing programming, I don't like typing out 2,000 lines of code to be able to do one analysis when I can run that exact same analysis in a GUI in less than 15 minutes. So if you want to get into the R stuff, you're more than welcome. I hope this code helps you so much. This is on GitHub. You can get all this code there, and you can change it, modify it to help you. If you don't want to do all the coding, please feel free to check out Simple Meta-Analysis. It is 100% free. You can get it on GitHub if you want to run it locally, or you can run it through the web interface on Shiny. The links to that are in the description as well. So that said, I hope this has been helpful for you guys. I'm sorry I'm a little bit more rambly tonight than usual. I think I have learned a lesson of maybe I shouldn't record videos on a Friday night after a long week of work. But you know, I really wanted to get this content out to you guys, and I don't know, I had fun with it, and as we're going through this, it's reminding me so much why I created Simple Meta-Analysis, because we're walking through all these steps, and I was swapping out these things as I eyeballed it and realized there was a mistake in there. And so, you know, they're all corrected now because I corrected them all in the video, and all those corrections are going to be pushed out to GitHub. So by the time this is actually on GitHub, all these corrections will be there. You don't have to make those corrections. And when I say you don't have to make those corrections, I mean you don't have to make the ones that you saw me make, where I was like, I had the wrong letter down here. I had VRVE instead of just the uppercase V. So you will need to swap out your variables, your data files, etc. So this pretty much wraps up this video. If you guys have any questions, please feel free to include them, to put them down in the comments. If this has been helpful for you, please like and subscribe to help support the channel. I really appreciate it, and I hope you guys have an absolutely wonderful weekend. Thank you, and I'll see you guys in the next video.